Thanks for joining me this afternoon. I would like to share with you how my mother-in-law got me thinking about primes. My mother-in-law, she won't own a smartphone because she doesn't want her information out there. And in light of recent events, maybe she was right about this. I don't know, maybe the NSA is watching us, maybe not. But to take it a step further, she won't make purchases online. And here, we know she's incorrect for sure. Because cryptography that uses large prime numbers is responsible for protecting our most sensitive information on the web. And although this presentation doesn't delve into that topic, I did just want to share with you how my mother-in-law got me thinking about primes, and I thought that I owed her some thanks for providing me the motivation for this presentation. So I want to speak on a potpourri of number theory topics, really, in particular perfect numbers and their relationship to a type of prime number called Mersenne primes. Mersenne primes are named after Marin Mersenne, who was a 17th century French mathematician and philosopher. He started a theologian, though, and he was a Roman Catholic friar. He taught theology and philosophy until 1618. But in 1620, he settled in Paris and studied math with the likes of René Descartes and Etienne Pascal. Mathematicians generally, and number theorists in particular, like to play with numbers. So let's imagine that Mersenne was playing with perfect numbers one sunny afternoon. A perfect number is a natural number that is equal to the sum of its proper factors. The proper factors of a natural number, all of its factors except for the number itself. So the proper factors of 6 are 1, 2, and 3, and lo and behold, 1 plus 2 plus 3 is 6. So 6 is a perfect number. In fact, it is the first perfect number. The next perfect number is 28. Its proper factors are 1, 2, 4, 7, and 14. And they sum to 28. So here's Descartes saying that perfect numbers are rare. And you can see by just this short list of 6 of them that they seem to be sort of spread out there at the end. In fact, the 6th perfect number is 8,589,869,056. So perhaps it's even surprising that we know that this number is perfect, right? I mean, makes me, how do we know that? But I hope by the end of this presentation that you see this number is actually dwarfed by some of the perfect numbers that we do know. So to be complete, we should talk about deficient numbers and abundant numbers. A deficient number is a natural number whose sum of proper factors is less than the number itself. For example, 8. Its proper factors are 1, 2, and 4. They sum to 7. 7 is less than 8. Therefore, 8 is deficient. We know that there are infinitely many deficient numbers because Euclid proved that there are infinitely many prime numbers. And any natural number of the form p to the k, positive integer, a natural number, is deficient. So for example, 5 cubed, which is 125, is deficient. Its proper factors are 1, 5, and 25. They sum to 31. And so 5 cubed is deficient. In fact, 5 to the 4th is deficient. 5 to the 5th is deficient. 7 to the 5th is deficient. Any prime number to a natural number is deficient. There are infinitely many primes, and so there are infinitely many deficient numbers. An abundant number is a natural number whose sum of proper factors is greater than the number itself. Example 12. The sum of the proper factors of 12 is 16. 16 is greater than 12, and so 12 is abundant. So a couple of neat things. If you look at the short list of perfect numbers we had here, you might have noticed that they're all even. In fact, no odd perfect number has been found, but no one has proven that they can't exist. So this is an open problem in mathematics. Does there exist an odd perfect number? We know that if there is one, it's extraordinarily large. We also saw from our short list that they seem to be rare. In fact, it's easier to find semi-perfect numbers. A semi-perfect number is a natural number where a subset of its proper factors sum to the number itself. So clearly all perfect numbers are semi-perfect because all of their factors sum to the number itself. But there are more. 12, the abundant number that we looked at, is semi-perfect because 2 plus 4 plus 6 is 12. And 2, 4, and 6 are proper factors of 12. In fact, if a number is semi-perfect and not perfect, then it must be abundant, because a deficient number can't have a subset of its proper factors add to the number when all of them don't sum to the number. So it has to be abundant. So did you notice in this list 6, 12, 18, 24, 36. Is that striking? No? They're all multiples of 6? Were you going to say that? Yeah, OK. Yeah, they're all multiples of 6. And in fact, if n a semi-perfect number and q a natural number, then nq is also semi-perfect. So this is cool because it gives us a way to generate semi-perfect numbers, and it tells us, in fact, that there are infinitely many of them, and also serves to show that there are infinitely many abundant numbers. If there are infinitely many semi-perfects, and every semi-perfect is abundant, then there are infinitely many abundants. So as an example of how this theorem works, the proper factors of 6 are 1, 2, and 3. Now if we take 6 and we multiply it by 2, then this new number 12 has the factors listed, a subset of which are all of these multiplied by 2. So 1 times 2 is a proper factor of 6 times 2. 2 times 2 is a proper factor of 6 times 2. And 3 times 2 is a proper factor of 6 times 2. So if we let n be semi-perfect and q a natural, then n must be the sum of a subset of the proper factors of n. And if we take n and multiply it by the natural number q, then we're taking q times a sub 1 plus a sub 2 all the way up to a sub k, where each of those is a proper factor of n. And then we just distribute the q, and we note that q times a sub 1, q times a sub 2, all the way up to q times a sub k, they're all factors of nq. So nq must be semi-perfect. So this theorem tells us that infinitely many semi-perfect numbers exist, and consequently infinitely many abundants. And although we don't know of an odd perfect number, we do know of odd semi-perfects. The very first odd semi-perfect is 945. I'm going to ask you to do some math. Can you find another odd semi-perfect number?
Can you define semi-perfect one more time?
Yes, semi-perfect number is a number whose where a subset of its proper factors sum to the number itself.
How about 2835?
2835, yeah, that's correct. 2835 is semi-perfect and it's odd. How did you find it?
Multiply it by 3.
Beautiful. Why didn't you multiply it by 2? Because then it would be even. So take an odd semi-perfect number, multiply it by another odd number, and you get another odd semi-perfect number. So that's a direct consequence of this theorem. OK, so it might seem that many or most abundant numbers are semi-perfect. And in fact, if a number is abundant and not semi-perfect, it's called a weird number. That's the name Yeah. 70 is a weird number. Its proper factors sum to 74, but no subset of them add to 70. And here are some other weird numbers. And again, look at the list. 836, 4030. They're all even, again. And in fact, every weird number that we know is even, and we don't know if an odd weird number exists. Another open problem in mathematics. Okay, so let's turn our attention back to the perfect numbers. 6, which is 1 plus 2 plus 3, is actually the third triangular number. There are triangular numbers just like there are square numbers. 28, which was the second perfect number, happens to be the seventh triangular number. The third perfect number, 496, is also a triangular number. It's the 31st. The fourth perfect number, 8128, is also a triangular number. It's the 127th. So 3, 7, 31, and 127. So there's Mersenne, and he's thinking about the natural numbers and maybe 2 to the power n, and then subtract 1. And those numbers 3, 7, 31, and 127 all happen to be in this list. They are all 1 less than a power of 2. Do you notice something else about them? They're all prime. They're all prime. In fact, Mersenne thought that maybe this method of subtracting 1 from a power of 2 might be a good way to generate prime numbers. And it's for this reason that we call prime numbers of the form 2 to the n minus 1 a Mersenne prime. So Mersenne came up with a list. He checked a lot of numbers. He came up with a list where he checked all of the powers of 2 up to 2 to the 257 minus 1. And his list included 2 to the 67 minus 1 and 2 to the 257 minus 1, both of which were mistakes, so they are composite. And he also left out a few numbers that were prime. He left out 2 to the 61 minus 1, 2 to the 89 minus 1, and 2 to the 107 minus 1. But that's, for a lot of work, 5 mistakes is not bad. I mean, this is 17th century, so. So his list did, in fact, include 2 to the 127 minus 1, which was verified as prime in 1876 and was the largest known prime for 75 years. It's also the largest prime ever found by hand. Okay. So as you look at this and you think about the number 2 to the n minus 1 and when it is prime, perhaps you noticed something about the power. In fact, when 2 to the n minus 1 is prime, the power n is prime. The converse is not necessarily true. So just because a number n is prime, that doesn't mean that 2 to the n minus 1 is prime, right? So every banana is a fruit, but not all fruit are bananas. So in order to prove that when 2 to the n minus 1 is prime, that n is prime, in fact, we're going to consider the contrapositive of the statement. And the contrapositive of the statement has the same truth value. So to find the contrapositive, we negate the conclusion and negate the hypothesis. So we're going to try to prove that if n is composite, then 2 to the n minus 1 is composite. And there's, there's a couple ways to do this proof. One, I think, is a little bit boring, and one I think is cool because you get to use base 2, and I figure if you can, why not? So we'll think of an example first. So 32. Well, 32 is 16 plus 16. And 16 is 8 plus 8. But 8 is 4 plus 4. 4 is 2 plus 2. And 2 is 1 plus 1. So let's take this equation and subtract 1 from both sides so that we have 32 minus 1 is equal to, well, we notice 2 to the 5th minus 1, which is 16 plus 8 plus 4 plus 2 plus 1. Each of those is a power of 2. We write that in base 2 as a string of 5 ones. So consider the contrapositive. If n is composite, then 2 to the n minus 1 is composite. Let n be p times q. Then 2 to the n minus 1 is 2 to the pq minus 1, which is a string of pq1s in base 2. Group p of them, factor them out. So then you have p1s right here, and then a string of q of these p minus 1 zeros and a 1. So example, 2 to the 8th minus 1 is 8 ones base 2. Factor out 2 of them. So you have this number 1, 1 in base 2 times this number 1, 0, 1, 0, 1, 0, 1, 0 base 2. Now this is 3 in base 10. And this is 1 plus 4 plus 16 plus 64. This is 3 times 85. 255 is composite. So what we show is if n composite, then 2 to the n minus 1 is composite. Equivalently, if 2 to the n minus 1 is prime, then n is prime. So the other way is to just factor it, which is, I think, a little bit more boring. But it does factor in this fashion. If you have 2 to the pq minus 1, it factors as shown. And there's an example here. 2 to the 9th minus 1. I just picked 9 because it's 3 times 3, which is composite. Is 5. This is 511, which is 2 cubed minus 1 times 2 cubed squared plus 2 cubed to the first plus 1, which is 7 times 73. OK, so we're almost to the moral of the story this afternoon, the coup de grace. We will show that if 2 to the k minus 1 is a prime, namely a Mersenne prime, then 2 to the k minus 1 the exponent, times 2 to the k minus 1, that Mersenne prime, is a perfect number. And moreover, every even perfect number must have this form. Equivalently, n is an even perfect if and only if n equals 2 to the power k minus 1 times 2 to the k minus 1, where 2 to the k minus 1 a Mersenne prime. So in order to prove this theorem, I have to introduce you to a function, perhaps a new function to you, called sigma. Sigma of n is a function that adds all the divisors of the natural number n, including the number n itself. So sigma of 1 is 1. Sigma of 2 is 1 plus 2, 3. Sigma of 3 is 1 plus 3, 4. Sigma of 6 is 1 plus 2 plus 3 plus 6. This is 12. So sigma is, well, did you notice that sigma of n has to be at least n plus 1? The factors of some number are at least the natural number n1. So this is actually important, that sigma n must be at least n plus 1. And if n is prime, then sigma p is exactly p plus 1. Why is that? The only factors of a prime are the number and 1. And if n perfect, then sigma n is 2n. And this is because sigma adds all of the factors of n, not just the proper factors. And when the number is perfect, the sum of the proper factors is n. And then we add n itself, we get 2n. So sigma n is 2n when n is perfect. So these 3 statements are going to be pretty important when we try to prove this theorem. So sigma n is multiplicative. And let me give you an example of a function that you know is multiplicative. So maybe f of x defined as x squared. X squared is a multiplicative function. So maybe f of 10. This is 10 squared, which is 100. But we can think of 10 as 2 times 5. So f of 2 times 5, I argue when f is x squared, is f of 2 times f of 5. This property is when a function is multiplicative, it has this property. And so this is 2 squared times 5 squared, which is 4 times 25, which is 100. So you see that the parent quadratic function, f of x equals x squared, is a multiplicative function. Sigma of n, also a multiplicative function. So for example, sigma of 30 is 72, but you can think of 30 as 5 times 6. Sigma of 5, well, that should be pretty easy for us to find because 5 is prime. And now we know that sigma p is p plus 1. So sigma of 5 must be 6. And sigma of 6 should also be pretty straightforward. It's got to be 12 because 6 is perfect. And sigma of a perfect number is twice that number. So 6 times 12, 72. So here's an example to provide some evidence that sigma n is multiplicative. So now we can show our main point. This theorem is biconditional, which means we need to show it both ways. We need to show that if n is equal to 2 to the k minus 1 times 2 to the k minus 1, where 2 to the k minus 1 is prime, then n is perfect. Also, we have to show that if n is perfect, then it takes on this form where 2 to the k minus 1 is a prime. So we start with this direction. We assume that n takes the form 2 to the k minus 1 times 2 to the k minus 1, where 2 to the k minus 1 is prime. We're going to show that sigma n is 2n, and then conclude that n is perfect. So because sigma n is multiplicative, we can say sigma n is sigma of 2 to the k minus 1 times 2 to the k minus 1, which is sigma of 2 to the k minus 1 times sigma of 2 to the k minus 1. Now, this one, sigma of 2 to the k minus 1, that's no problem. That's no problem because the assumption is that this number is prime. And if 2 to the k minus 1 is prime, then sigma of 2 to the k minus 1 is 2 to the k minus 1 plus 1, 2 to the k. So sigma of 2 to the k minus 1 is 2 to the k. The question is, what is sigma of 2 to the k minus 1? So 2 to the k minus 1 is a power of 2. And I argue that all of the factors of a power of 2 are all the powers of 2 before it, right? So just think about 32. Factors of 32, well, it's 1, 2, 4, 8, 16, and 32. So we see that all of the factors of 32 are all powers of 2. So let's just continue Well, we're going to sum k minus 1 here. We want 1 plus 2 plus 4, right, plus 2 to the k minus 1. This is a partial sum of a geometric sequence. And we can find the sum by taking the first term, which is 1, and multiplying it by 1 minus the ratio here is 2, and there are k terms. And we divide this by 1 minus the ratio, which is 2. So we have 1 minus 2 to the k over negative 1, which is 2 to the k minus 1. So sigma of 2 to the power k minus 1 is 2 to the k minus 1. And so sigma n in this case is 2 to the k minus 1 times 2 to the k. Do you notice that that's exactly twice n? So multiply this by 2. That adds 1 factor of 2 here. So now we have 2 to the k times 2 to the k minus 1. So it's exactly 2n. And so we know that if n takes this form, 2 to the power k minus 1 times 2 to the k minus 1, where 2 to the k minus 1 prime, then n must be perfect. Okay, so the other way is I don't know if this is easy, but the other way is not as easy. So I need a marker. Okay, so we want to show now, if n is an even perfect, then it takes the form 2 to the k minus 1 times 2 to the k minus 1, where 2 to the k minus 1 a prime. Okay. So let n be even perfect. Then n is 2 to the k minus 1 times m, m an odd natural. So this is legal because n is even. It's got to have some number of powers of 2, right? It's got to have some multiples of 2. We just factor those out. We have m odd. So sigma n is sigma 2 to the k minus 1 m, but because sigma is multiplicative, so this is sigma 2 to the k minus 1 sigma m. This guy we just computed, right? This is 2 to the k minus 1, so sigma m. Now, we know that n is perfect, which means sigma n is 2n. So sigma n is also 2n, which is 2 times 2 to the k minus 1 m, which is 2 to the k m. So transitive property of equality. Yeah? If A is B and B is C, then A is C. Namely, 2 to the k m must be equal to 2 to the k minus 1 sigma m. This tells us that 2 to the k minus 1 divides 2 to the k m but it cannot divide 2 to the k. It's 1 less than 2 to the k. So it must divide m. So 2 to the k minus 1 divides m. Let m be 2 to the k minus 1 times natural number n. So let's go ahead and substitute 2 to the k minus 1 times n in for m. So I have 2 to the k times 2 to the k minus 1 times n is 2 to the k minus 1 times sigma m. We see that the 2 to the k minus 1s cancel. We have what? We have 2 to the k n. 2 to the k times n is exactly sigma m. But sigma m must be greater than or equal to, well, m plus n divides it. N divides m. Here, sorry, n divides m. But m plus n is 2 to the k minus 1 n. That's m. That is m plus n. Distribute this n. We have 2 to the k n minus n plus n. 2 to the k n minus n plus n is precisely 2 to the k n. So do you notice that you have this inequality squished between these two numbers that are exactly the same? This tells us that sigma m is exactly m plus n. So sigma m is exactly m plus n. I'll have you note that it's not m plus n plus 1. And so n is 1, and m is prime. So n is 1, and then sigma m is m plus 1, and so m is prime. And if n is 1 and m is prime, then m is 2 to the k minus 1 times 1, or 2 to the k minus 1 and prime a Mersenne prime. So that makes me extraordinarily happy. I don't know if yeah, so this direction was perhaps not as easy as the other way, but it does.
The only question I have was, how did you go from the m? How did you put the plus n there?
Okay, so because n must divide m, as shown here, so n must be a factor of m, but m must also be a factor of m. So sigma m has to be at least m plus n.
I actually was thinking it had to be plus 1.
So it turns out that n happens to be 1. Yeah. So what does this look like? Well, now that we know this theorem works, we can think of an example of Mersenne prime, for example, 2 to the 5 minus 1. This means that 2 to the 5 minus 1 times 2 to the power 5 minus 1 must be perfect. That's 31 times 16, which is 496. A couple of other examples. 2 squared minus 1 is 3. It's a Mersenne prime. Times 2 to the power 2 minus 1, which is 2. That's 6, the first perfect. 2 cubed minus 1 is 7, a Mersenne prime. Times 2 squared, 7 times 4 is 28. The second perfect number. So we know that there are as many perfect numbers. So we know as many perfect numbers as we do Mersenne primes. And we don't know if that set of numbers is infinite or not. The search for Mersenne primes has really a cool history, some of which we've already seen. Mersenne was definitely not the only one to study primes of the form 2 to the n minus 1. In fact, we know that Euler did, we know that Fermat did, among others. Like I stated earlier, 2 to the 127 minus 1 was the largest known prime until 1952. It's the largest one that was ever found by hand. In 1952, Raphael Robinson found the 13th through the 17th Mersenne primes, and by 1971, we had found 24 Mersenne primes. The 25th Mersenne prime was found in 1978. It's 2 to the 21,701 minus 1. It has 6,533 digits. If it were typed so that each digit were 2 millimeters, it would be almost 43 feet. That's not the coolest thing about this number, though. I think the coolest thing about this number is that it was discovered by Landon Kurt Knoll and Laura Nickel, 2 high school students. They also found the 26th Mersenne prime a year later. It's 2 to the 23,209 minus 1. Both Nickel and Knoll work as computer scientists now. Knoll was actually famous for another prime found in 1989. It was famous for being the largest prime found that was not a Mersenne prime. All Mersenne primes found post-1996 have been found using a computer searching project called the Great Internet Mersenne Prime Search. It has the unfortunate acronym GIMPS. I wonder if I can bring you there. Can I click on this? So if you go to mersenne.org, I hope this doesn't. No? OK. So if you go to mersenne.org, you can sign up to be a part of the Great Internet Mersenne Prime Search. It takes a lot of computing power to try to find a Mersenne prime. And so the Great Internet Mersenne Prime Search is a network of computers. And if you sign your computer up, it costs about the same as what it costs to run a light bulb for a year. And what it does is it will run in your computer the program to help find a Mersenne prime, and it will only do so when you're not actively using your computer, so it won't take up any of your computer's computing power when you're using it. So I'll talk more about this in a second, but a year ago, a Mersenne prime was found, and the discovery is eligible for $3,000. So hey, there's some money attached to it. It has to meet some criteria to be eligible for.
To find it?
No, just if your computer finds the next Mersenne prime, yeah, you could be entitled to an award, a reward, depending on if it meets certain conditions. I think it has to be some number of digits and some other things. You can probably find more information at mersenne.org. So as we saw on the website, the 48th Mersenne prime was discovered last year in January. It's 2 to the 57,885,161 minus 1. It's got 17,425,170 digits. If it were typed with each digit being 2 millimeters, it would be over 21.5 miles. Anyone a runner? Anyone do some marathon training? So I did a marathon once, and I did marathon training. And I'm just thinking, like, after 20 miles of running, I still haven't covered the largest Mersenne prime. That's crazy. Fans of George R.R. Martin? Anyone read Game of Thrones? OK. So if this number were written in a book, it would take up the entire 5-volume set of George R.R. Martin's Song of Ice and Fire, all of it twice. Okay, so why? Why search for the next Mersenne prime? Why search for the next perfect number? Well, for primes, it does help with security. It does help with cryptography, but I don't think that can be all. I don't know if that's the driving force. Certainly money helps, and you might get some press. But I think naturally humans are explorers, and what greater landscape is there to explore than the landscape of math? And I teach high school, and last year one of my students told me this really haunting quote, and I don't know who said it originally, but he said they heard this quote that said everyone dies twice, once physically when they stop breathing, and a second time when someone says your name for the last time. And since I teach high school math, you know that I teach geometry, and you know that I teach the Pythagorean theorem every single year. And as long as we study math, we're going to be uttering the name Pythagoras. So Pythagoras has achieved some sort of immortality, some sort of mathematical immortality. So go home, register your computer for the great internet Mersenne Primes search, and maybe you will cross your fingers and maybe you will have some mathematical immortality. Thanks.